Hello, everyone. Thank you for joining this seminar series organized by the Empathic Computing Laboratory. I'm your host, Aladdin, and our distinguished speaker for today is Chris Harrison, who is currently an associate professor at Carnegie Mellon University, and is leading the Future Interfaces Group. Dr. Harrison investigates novel sensing and interactive technologies and has been influential in the HCI community. He has done a lot of research since 2006, if that's correct, or 2004.
Sure, something like that.
The title of the talk is Why Are Smart Devices So Dumb? The talk will be roughly an hour, followed by a brief question and answer sessions. Thank you for joining us, Chris.
Yeah, thank you everyone for coming. Especially for people in other time zones where it might be fairly early in the morning. Let me just go ahead and share my screen here. Given the size of people that are on, I think if people have questions, do interrupt me. It's a little hard in the Zoom interface sometimes to see if people are raising their hands and such. So feel free to unmute yourself if you have a really pertinent question that it'd be useful to know. If not, we'll have plenty of time at the end to go through things. So as was said, and thank you for that introduction, I'm going to talk about, why are smart devices so dumb? We use this smart name on a lot of different appliances, from toasters and refrigerators and so on. And, for most of the part, they're not as smart as we might want them to be, and certainly not smart in the same way a human might be smart. But before we get into that, I wanted to tell you a little bit about my lab and also, what my lab does, what our process is. So as was mentioned, I run a group at CMU called the Future Interfaces Group, this nice broad purview thinking about what the future of interaction is going to hold. And that is inside of an institute called the Human Computer Interaction Institute. And that is inside of a school of computer science. So we don't just have a department of computer science at CMU, but rather a school of computer science. And there's about 250 faculty dedicated to the pursuit and advancement of computer science. And about 35 of those faculty live in this HCI department. And what my lab does is really, I would say, kind of three pillars. One is signals and sensors. We want to get interesting inputs in order to build new computational experiences. It's hard to do that with a keyboard or just a touchscreen. We want to think about bringing in new avenues to build these new technologies. It's not going to be able to build a next generation interface purely on those classical methods. And then often, as you get off into more exotic sensors, is we're going to need to make sense of those signals, right? Is that humans are not like a button on a keyboard, which is either pressed or not pressed. There is no other state that a keyboard can really express, but humans are messy. The fact that I'm gesturing right now, I'm moving my hands just, as a professor, I feel like it's almost mandatory to gesticulate like this. But you can imagine in my room, if I had a smart thermostat on the wall, and it's going to be using computer vision to look at me and make a decision, is Chris waving at me? Does he want me to increase the temperature or decrease the temperature? It's looking at my hand gestures, trying to respond, sort of like what a human might. And it's not a I'm 100% or 0%. These gestures are probably low percentage, maybe 5%, but it's not an absolute. There's a spectrum of whether or not I'm addressing it and if I want to go up or down. And so we need methods to be able to resolve that ambiguity that's inherent with humans, and machine learning is a great complement to that. And very similar to that is the computer vision, machine learning in the visual domain. And then finally, a lot of what we do is requires physical prototyping, both in electronics, but also in the form of things. If you want to simulate what a future AR glasses is going to look like, or a future car dashboard is going to feel like, you can't show people on a laptop, right? You couldn't have shown people how cool an iPhone or smartphone was going to be, and you showed it to them on a desktop computer. Sometimes you have to put technology onto people's bodies, out into the real world. And so a lot of what we do also is about actually making the thing. It's not just software, but hardware and industrial design as well. Now, in terms of ethos, right, not just the skills that we draw on, but in terms of ethos of the lab, is we often approach domains in human-computer interaction thinking about sort of what are the computational ingredients that we might be missing that could allow us to essentially bake whole new computing experiences, or at least better versions of current experiences. So this is sort of like, previously you could bake a really delicious cake, but then, someone shows up with chocolate, and now you can make an even better cake, or at least a better cake for some people. It's not that you brought all the ingredients. You might have just brought one extra ingredient to the table, but now you can fundamentally make something new. And I like this analogy because it takes a lot of ingredients to make a cake. So in our case, in my lab, we're drawing on advances from a lot of other fields like natural language processing and computer vision and cloud compute, embedded compute, sensors. And we're drawing on those things, maybe not making advances in most of them, or combining them in interesting ways in order to make breakthroughs. Now, the other thing we do in terms of sort of ethos is we look a lot at historical trends. Now, people often find this kind of strange that someone whose whole lab has the word future in it, that they're looking into the past. But I think it's actually really important in order to see trajectories in computing. And so myself, a lot of my papers will start with some sort of historical kind of background, talking about the stories. I'm citing papers sometimes from the 1400s or even before that to set the stage, because I think a lot of these ideas have long roots. They go back in time, and just to look at it like it popped into your mind is actually not giving an idea justice. So today, I'm actually going to go through sort of this exercise with you a little bit, and I want to play a short clip to set the scene. So this gentleman you're seeing on the screen right now is Professor Coons, and he is going to describe, I'll play a short video. He's describing Ivan Sutherland's Sketchpad system. So if you're a student of HCI and you've never heard of a Sketchpad, you should probably Google around, read the Wikipedia article. Very seminal system, early computer-aided drawing program, CAD program. If you're not familiar with it, it's not critical to know, but I want you to listen about what Professor Coons is saying about computing of the past. So this is the 1960s. We're talking about 60 years ago, and listen to how he's describing the past of computing from the vantage point of the 60s, and also the future of computing, again, but from the 1960s. So let's just listen here.
But little by little, he will begin to investigate ideas, and the computer and he will be in cooperation, in the fullest cooperation in this work.
Well, now, how is this different from the way the computer has been used in the past to solve problems?
Well, the conventional way, the old way of solving problems with the computer, has been to understand the problem very, very well indeed, and moreover to know at the very outset just exactly what steps are necessary to solve the problem. And so the computer has been, in a sense, nothing but a very elaborate calculating machine. But now we're making the computer be more like almost like a human assistant.
Okay, so he's talking about the old way of using computers is to treat them basically like a very elaborate calculating machine, and that you have to know from the outset how exactly you're going to solve that problem. And I think if we're being honest, that's still what computers are today. They're very elaborate calculating machines. And if I want to use them as a tool to get something done, I follow actually a pretty prescribed set of steps. If I want to look up how to, apply a filter in Photoshop, or even, bake pancakes, whatever, make pancakes in the morning, I know what to do. I go on Google, I say, pancake recipe, I'm gonna go on some website and pull it down. It's actually fairly mechanical. Most of what we do is fairly mechanical. Even a lot of the creative tasks, like using Photoshop or Illustrator or Premiere, whatever your favorite creation tool is, I actually think are fairly mechanical. It's not all that different from how you might go building a house, or even, painting a new piece of art. And that's a process that you go through with a set of tools. Now, this second quote, I think, is actually hinting at something much deeper, and that is that the computer and the user will be in the fullest cooperation. And I really like that word, because that's not how you describe a tool. You don't cooperate with a hammer. You don't cooperate with a paintbrush, right? That's just a weird way. You use a tool. You don't cooperate with a tool. And I think back even in the 1960s, people were thinking of computers as something much, much more. And as Professor Kuhn says, much more like a human assistant. So I actually prefer a term they use later in this video. It's a very long video, but later in the video, they actually refer to computers as a coherent partner, which is a great term. And it's obviously echoed by a lot of early computing pioneers like Engelbart and Bush and Licklider and some other people that maybe you studied in your classes. So I think we're very much stuck, and still are, in a kind of a computers as a tool phase of computing. That's like from Babbage all the way to now. Is computers are really amazing. Don't get me wrong, they're amazing and they're hugely successful and very useful, but they're still tools in much the way that a hammer is fantastically useful and successful, and that's okay. But we're nowhere near this rather intriguing idea of a computer as a coherent partner, almost like a partner in crime while you go about your tasks. So if we go back to kind of my ethos of my lab, what are these computational ingredients that we're missing to bake this new delicious, cake of computing? Well, I would say we're missing fundamentally this ingredient about how to make a computer as a partner. And a really important ingredient that we're missing to achieve that future is context awareness. For those of you who are not familiar with this term, it's probably not all that unsurprising from the words it's used, but essentially it's to be aware of one's surroundings. And that includes physical facets, what's going on physically around you, and also social dimensions. And I think if you really want to build a computer as a partner, it has to understand these things. Human assistants understand context awareness. They are very contextually aware. That's what makes them, makes a really good assistant. They're almost one step ahead of you because they understand the context and your mental state so well. But computers really have no idea about this. So, here are some example contexts, right? You might have in the top left here, you might have a student that's at home, focusing really hard to finish an assignment. You might have a business person in an office that's trying to close an important deal. You might have a very angry or frustrated driver, all the way to a family dinner, right? These are all very different physical spaces with varying constraints, and they're also very different social settings. There's professional settings to family settings to being solo and focused on a task. And so I would kind of ask you, if you did have a dedicated human assistant that kind of followed you around, okay, you're so fantastically rich, you just had like an entourage that followed you, would that human assistant react differently across these different contexts? And I think the answer is absolutely, right? They might get a piece of news, on their phone, but they might decide to withhold it because they know that you have to finish your homework and it's really not that critical to interrupt. Or maybe it's relating to that dinner. Maybe that you've cooked a fantastic dinner, for a family holiday, and a guest is running late, or the food is burning. And even though you might say, well, a family dinner, that's got to be at the maximum level where interrupting has an incredible social penalty, because that's so pertinent, they might actually decide to interrupt because it's highly relevant. So this is very complicated. It's not a yes or no or 1 to 10 scale. There's a lot of dimensionality here, and computers get it entirely wrong, right? Humans do it pretty well. Computers do it entirely wrong. I would argue that they actually interrupt us and distract us much more than keeping us focused. And the idea of a computer sort of stepping in to proactively help us when we might be going down a wrong path, like baking a cake wrong or something like that, that's basically science fiction is today. So they're really good assistants. They're really good tools, but I'd argue that they're pretty bad assistants. And that's because they know very little about the immediate world around them. They don't know. You're like Alexa or your smartwatch or your phone. They don't know that you're having dinner. They don't know the dinner is burning. So how can we really ask them to be context aware when they don't even know these very rudimentary things? That's a very tall order. So, here is that case, right? This is the state of the art in smart speakers, right? Is that you have it sitting on your kitchen countertop and it has no idea it's even in the kitchen. It has no idea that you're making dinner, right? Despite the fact it's supposed to be a smart kitchen, kind of helping device. And even more, I think, kind of strongly is this, smartwatches, right? The smartwatch, it is literally living on your hand. But it could tell me way more about the traffic conditions in Auckland or in Sydney than it could, and the weather. And it could even I could ask it, tell me the entire history of Auckland. It can read that Wikipedia article for 20 minutes, all the intricacies of the entire, country and city. And yet it knows nothing about my hands, despite the fact they're 10 centimeters away. So there's this weird impedance match that it can tell me what the traffic is at, or whatever, how busy a cafe is on some corner in, Auckland, more than it knows about my own hands. So they're smart in some ways and incredibly dumb in others. So something is kind of broken here. So I think if we want to build up to this vision as computers as partners, we need to bootstrap them starting at the bottom. And we need new approaches for computers to really understand and sense their surroundings, on top of which we can build models of context awareness. And if we're successful, it's going to be a really crucial ingredient that's going to enable that kind of future of computers as partners. So having set the stage here, I'm going to tell you about some of the research my lab has been working on in this research area. And I'm not going to go into tremendous depth on any one project because I want to show you purposely breadth. But again, people are welcome to ask questions. And certainly at the end, I think we have something like 25, 30 minutes to go through questions if you want to follow up on specific details. So let me start with an early project. This actually goes back to 2016, but it's actually a project that's continuing to this day. And it's this notion of synthetic sensors or general purpose sensing. And that's actually now becoming standard practice in kind of IoT sensing and in the industry. Now, here's the technique we took. Here's sort of the premise we took. We said, look, we know that these sort of like IoT style sensors, these little boards that have sensors on them, and you can kind of stick them around your house, stick them on your ceiling and so on to sense things like occupancy and appliance use. Very cool idea. And they could be made low cost. And but we saw there was a lot of variety in industry. Some sensors had really good things for environment sensing, but nothing else. Some had really good things for sensing water in your basement, but couldn't sense if you were in the room or not. And so we did an inventory of all the different sensing systems that were out at the time, both industrial ones and academic research systems, as you can see by this kind of like plot here. And we said, well, look, we want to find out what sensors are important and what sensors aren't important. So let's just take a union of every sensor on this list. But importantly, you'll see that we don't include the camera. So this is the one sensor we said, do people really want a camera in every room of their house? Probably not. So let's see what we can do with every other sensor we could essentially order on an electronics website. And so this is what the sensor board looks like. A lot of these are multi-sensor chips. So we have a single sensor for temperature, barometer, humidity. So a lot of environmental sensors. We have a light sensor for measuring not only the illumination value, but also the color of the light, which turns out to be an interesting dimension. For example, when you're watching TV, the color tends to actually change in the room quite dramatically. And that's very distinctive of you watching TV. Color doesn't change when you're microwaving, some food for lunch. And here's actually what that board looks like in reality. So in this case, we have USB on it, but you can imagine that it would just have wall plugs. This just was ease of deployment and programmability. But fundamentally, think of this as a sensor that you plug into your wall. Now you might think, well, hold on, isn't it gonna be a lot easier to sense things if I take that sensor and I stick it to the object that I wanna sense? If I have a coffee machine and I wanna know how many times I turn it on to make a coffee, it seems like you wanna stick it right on that thing. And that's absolutely true. You're always gonna get the best signal by sticking a sensor to the thing. But then you have to either run wires everywhere. I think that's pretty much a non-starter. That's gonna cost a lot of money and it's very ugly. Or you're gonna have to go around and put in batteries. And so what we did is we wanted to know how bad was this problem going to be. And we kind of inventoried typical houses and we looked at how many facets you'd want to monitor, how many things in your house would you want an Alexa or a Google Home or a Siri to know about. And you want to know things like, is there a window open? Is the dishwasher on? Is the laundry machine going? Is the TV going? Is the microwave going? Is the gas on the stove? Is the garage door open? Is my front door open? Has the mail arrived? Is there a fan running? AC, if you make a whole long list of all the things in your house, rice cooker, blender, and so on, you end up with about 50 to 100 things that would be kind of useful. If you really have a super intelligent home, it should probably know like the stove is on and things like that. But if you have, let's say 100 facets, you want to know every door in your house, every faucet in your house, and so on, are you going to run around and replace 100 coin cells every 3 months? Probably not. Even if you get that to a year, that's pretty damning. So we decided instead is two things. One, let's go with wall power. We want people to plug this in and never have to think about it again. But number two, it also means we have to be much more clever with our sensing. We want to have ideally one sensor per room. So if you have 10 rooms in your house, you need to buy 10 things, not 100 things. But we have to be more clever with the sensing because now we're not physically attached to the objects that we want to sense. So instead, we use this array of different types of sensors to kind of listen, not just with audio, but listen in terms of photons and humidity and so on in the environment to try to do classification. And it turns out you can do it. So here's just a short clip here. In this case, the sensor is just kind of here behind the faucet here on this wall. And this is one of my PhD students, now graduated, Gerard Laput. And he is going around and you can see he's just turning on different things, microwave, coffee grinder, blender, faucet, and so on. And this one sensor for the entire room can actually detect all these things are going on without having instrumented them or changed them at all. But here it is in the bathroom. The sensor's right here. You can see the classification live. So I'm not going to go through this whole video. It's very long. What we really wanted to show, and I encourage you to watch the full video if this is a topic you're interested in, is that a single sensor is almost like a Swiss Army knife, that you don't need to have a special, smart sensor for your furnace and a special sensor for your smart fridge and so on, but rather you have this sort of jack of all trades sensor that you just plug it in the room, leave it, forget it, and it works just fine. And again, you kind of buy a 10-pack of these from your local hardware store, one per room, maybe get the cost down to $25, and now you have a smart house that can sense all of those 100 things. So everything you're seeing in this video is what we'd call a binary sensor. It's a first order synthetic sensor. It's basically on or off, microwave on, microwave off, faucet on, faucet off. That's actually not all that powerful. It doesn't kind of get us to the level of semantics we really care about to make actionable context-aware decision. So we just call those first order synthetic sensors, but you can actually go to higher order ones that build up from low-level inputs. So what you can see here, this is in my lab, we have a sensor in the room and it can hear, I heard a towel come out, I heard a towel come out, but there's a second level sensor that's actually counting the number of towels. It has a notion of state and knows that every time it gets refilled, there's 500 towels. Same with this, there's a sensor that's monitoring the flow, but then there's a second order sensor that lives above that to measure total cumulative usage, which you can imagine to promote things on social media to be more sustainable, for example. And even complex objects like the state of a microwave, right? There's door open, door closed, defrosting and so on. Again, you can have individual low order sensors that says, I heard the door open, I heard the door close. Each one of those are binary. And you can essentially use a state machine to model the complex behavior of something that's a bit more multifaceted, like the microwave. And of course, what's interesting here, and what this is the research that we're really continuing today, is that you don't have to stop at second order sensors, right? You can keep going up to third order sensors, fourth order sensors, fifth order sensors. You can imagine this kind of web of things that climb up this ladder to make these this is why we call them synthetic sensors, is that you have these essentially virtual sensors, right? You could have a sensor called, is the family eating dinner? And the sensor output is true or false. It's almost like a physical sensor, but actually it's taking in data from activations of how often the refrigerator is being open and closed. What's the ambient level of chatter? Based on occupancy readings or humidity readings, we know that there's 5 people in the room, et cetera, et cetera. So you can imagine that you have 20 different kind of second order or first order sensors that feed in through this kind of web of higher and higher level semantics. You have, is family present? Is dinner happening? And then is family and dinner happening? And it goes up and up, which is what humans are functionally doing to have these. Again, it's just a sensor. You can subscribe to this sensor. They can say, when it is family, dinner, holiday, that I can put on, whatever, family, old tunes, music on Spotify, whatever it might be, and build much more complex behaviors. That'd be impossible with just low-level sensors alone. So very meta things like, is Chris busy right now? There's no sensor in the world that does that, but you can imagine constructing that, and especially having deep learning constructed out of these low-level primitives. So this is the sort of process that we want to follow in this research. Now, this project is still very much alive, even though at this point it's more than 5 years old, is we've actually just finished a massive deployment led by Professor Agarwal at CMU. And this new building that actually just opened, the gates are gone now and people have moved in. There's every room in this building has been instrumented with one of these sensors. So there's about 350 of these sensors in total. It's in every room except the bathrooms, even though there's no camera on there, just for extra privacy protection, we didn't put it in the bathrooms, but pretty much every other room in this building has one or more of these sensors. And it's to be a test bed to probe the future of what does it really mean to have a smart building? I would argue that there's very, very few, if any at all, smart buildings around. We're trying to get to that future. I would argue that just because you have like a smart elevator bank that is slightly more efficient, that's not really all that smart. So this is a test bed to really dig into what does it mean to have a smart building, and also probe a lot of very important questions like, what does it mean for privacy, right? This is a hugely important issue of our time. How do you balance, having a more sustainable, reactive, and comfortable, work experience while also preserving occupant privacy? Really careful thing that has to be done very well. So moving on to another project, again, we're kind of whirlwinding this a little bit, is a project called Ubacoustics. Now, one of the things we did, one of the reasons why we included so many sensors in synthetic sensors, humidity, temperature, barometer, compass, humidity, Wi-Fi strength, EM radiation, this whole long tail of things, is we could actually rank order how useful those sensors are, looking at basically information power from a machine learning perspective. So you can say, humidity sensor, not that useful, but for example, we had a microphone, really an acoustic sensor on that. We never recorded any raw audio. But we wanted to see, is acoustic information more powerful? And it did actually turn out to be the most powerful thing. So acoustic information came out on top, followed closely behind by vibration data as captured by an accelerometer. But really what it understood was the power of sound for contextual awareness, that when humans perform activities like making dinner, reading a book, whatever, taking out the trash, opening the front door, delivery person ringing your doorbell, they make sounds. It's very hard to move around this physical world without, making vibrations, making sounds. And so we said, well, can we do sort of what we did in synthetic sensors, but only use sound? That would really reduce the cost of the board. So we can actually run a little experiment here. I'm going to play a very short clip. And if you want, you can close your eyes and listen to the sound over Zoom, and you can try to be the machine learning classifier, try to guess the activity. So here we go for this experiment. So close your eyes and see if you can name, kind of recognize what these different human activities are. So the order there, if you try this experiment, was chopping some vegetables, mixing in a bowl, turning on a vacuum cleaner, typing on a keyboard, and then brushing one's teeth. And we found that when we ran a study on this, that if you just give humans audio, they can be around 90% accurate, which is pretty good. They're not 100. Humans are amazing audio processing machines, but they're not even 100% accurate. But you can imagine that hopefully you got some of those correct. We can see that Mortiz got one or maybe two close. So again, audio aside, and if I gave you also some extra context, like you were in a living room, or you were in an office, or you're in a bathroom, you probably would be able to to figure it out with a much higher degree of confidence. So what we imagined in these, it's obviously smart speakers, for example, have really good microphones. In fact, they have microphone arrays. You're getting it compressed over Zoom and probably not with stereo. But something like an Alexa or a HomePod has a really high fidelity microphone array. And so we sort of imagine in the future, maybe what you can do is just parameterize, just drag over what you want your Alexa to know about, your smart speaker to know about. You can say, I want you to listen for baby crying. I want you to listen for doorbell. I want you to hear, when my dishwasher is finished, when the microwave is running, and sort of opt in. You can just sort of drag and drop this in. And the way we did this, just to give you some detail behind the scenes, is we actually leveraged professional Hollywood sound effect library. So CMU has a great film program, and so they have licenses for these big databases of sound effects. And what we were able to do, because those sound effects are so nicely and professionally recorded, there's no motorcycle going through the background, or they're all nicely, cleanly labeled, cleanly segmented, unlike downloading sounds off YouTube, which is another common approach. You can actually take those very nicely curated sounds, which often don't even have any echo. They're kind of reverbless. They're done in sound rooms often. And they tend to have actually thousands of sounds. You'd be amazed. Like, when you type in blender, there's like 1,000 blender sounds, 1,000 toilet flushing sounds, thousands of baby crying sounds. Because, when people are putting together a Hollywood film, they really do look for like the perfect, sound for that scene. And so they've recorded these unbelievable data sets going back, into the 1970s. And so we can take those very nicely curated sounds and without any reverb, and then we can actually, called like data augmentation. We can take that sound and project it into virtual environments. We can take that sound and say, what does that sound like in a small toilet, in a large kitchen, in a amphitheater, in an office with carpet, in an office with wood floors? And then we can actually also, on top of that, mix in different background sounds. So, people chatting, a printer running in the background. And so from one single sound effect, you can typically make a few hundred or even 1,000 variants of that sound effect. And of course, we have 1,000, different toilet flushing sounds. And so now we get, 100,000, sound samples to train deep learning on. Yes, kind of few shot. And so so in the end, this data set was really useful. And what's happening behind the scenes here is we're dragging over this thing, it's training a model, and it's able to learn. And so this is purely now with just sound. So in this case, you can imagine a smartwatch. It's listening with the sound effects. And it hears that you're coughing a lot, and it says, do you want to kind of go in for maybe a COVID test? And your smartwatch is now doing this proactively, right? This is not, I have to launch some app and so on. This is my smartwatch is now waking itself up, much more like a human assistant, saying, hey, I've noticed this. Maybe you want to find a local clinic, right? Here's another example. Again, we're using a little IoT sensor here on the wall, but it's monitoring all the equipment in our lab. So it's listening to, how long the drill press has been running for, laser cutter, and so on. And it's just accumulating the amount of time that they're running. And so you can see, look at the CNC mill. No one serviced it for 34 hours. Probably time for someone to come in and check the quality of the bits and the motors and oil it up, whatever it might be. But actually, this next example is my favorite. This is turning on a drill press, and the phone is waking up, and it says, don't forget to wear your safety glasses, when you're using power tools. And moreover, because it knows it's a drill press, it can actually infer the RPM. So in this case, it says I can tell that the drill press is running at 3,100 RPM, that's ideal for softwood. Now, it may not know that you're cutting a piece of aluminum or acrylic or something else. We don't have computer vision here. It has to do it purely with sound. But you could look at your phone, which again has woken up. It heard that it was running, and it has woken up and basically is making this recommendation to help you do your job better. This is much more like a coherent partner. This is like having the shop manager looking over your shoulder and saying, hey, this doesn't seem like the right speed. Let's look up. Oh, we want to be at 4,000 RPM to cut a piece of plastic. Okay, so moving on, talking about how you might actually train these things, one thing we did find is that even though we had these really large Hollywood-style sound effect libraries, is that it wasn't quite as good. It got to kind of like 95% accuracy, 90% accuracy when you trained it on all these sound effects and you took it to someone's actual kitchen. But really, there was nothing better, nothing beat, actually collecting data for that person's blender, in their kitchen, that person's toilet, in their bathroom. When you have the actual object in the actual environment with its reverb and impulse function and so on, that lets you get to much greater accuracies, really to approaching 100% accuracy. So we kind of revisited Ubiacoustics just last year, and we did a project called Listen Learner. And this is one-shot kind of labeling for activity recognition. So here's the premise that we want to, you put a smart speaker, and it could be a smartwatch, whatever, some sort of computer with a microphone in an environment, whether that's traveling with you like a phone or in your kitchen. It can listen to the activities that happen around you. So you can listen to the sounds here. This is sound only. There's the smart speaker on the table. And you can see it's projecting into a very low dimensional state here, these little white dots. It doesn't know what that sound is, but it heard something that sounded different. Now the user's sort of clinking together silverware. That sounds very different from cutlery. Or sorry, then chopping vegetables. So it's clustered those in a different spot. You can see these emerging clusters forming. Then the user's going to put something in the microwave. You see there's now a new cluster on the left there. And at some point, it's going to make a decision that it wants to know what that sound is.
What was that sound?
That was a microwave.
And now you'll see it's going to label that cluster. So this, in this case, is the sound of the microwave running. Kind of has this, humming sound that's fairly unique. And in particular, the reason why it asked about this cluster as opposed to the other two clusters is that it was a very tight grouping of very similar things that was very far away from other clusters. So it was a distinct cluster. Again, it had no prior knowledge. There's no training behind the scenes here. It's just listening, almost like a child, listening to an environment. And it knows that it sounds different, and it prompts the user saying, just tell me what that is. And it says, that's the sound of a microwave running. And then it can not just label that one new data point that came in, but everything in that cluster. We make the assumption that you can go ahead and label that. In this case, we just ran this experiment for 5 or 10 minutes. But imagine this has been running in your house for a week or a month or a year, and it's finally learned to separate all the different sounds in your kitchen. So if you let this run long enough, this is what the labels will look like. Now, again, we're projecting a very high dimensional space, hundreds of dimensions down into a 2-dimensional plane. So you kind of imagine this in 3D. Some of these clusters that look like they're stacked would actually be separated in 3-dimensional space, and even more so in 600th dimensional space. And so you can actually get to labels that are pretty good. Some things, again, there's always incidental noise that can confuse things. But overall, it actually can learn all the main things just, after, just, a couple tens of minutes, living in your kitchen for a week can normally bootstrap it with all of the objects. And again, we found that people are pretty willing to sort of almost teach it like a child. Even when we found that even when it makes mistakes, it says what you can even prompt it as if it's confirmatory, like, there's a new dot has been added to the cluster that is the microwave, but it's a little far out. So the thing can actually ask, is that a microwave? And you go, I can see how you'd think that, but it's actually the sound of a faucet running, and then say, oh, thank you, and then it kind of refines the clusters based on that knowledge. And we found that users were not super annoyed because, again, the interruption was pretty low, that people were sort of willing to give it a bit of latitude, like they're teaching it like a child, like an infant learning words for the first time, which was a really interesting effect. And then it really becomes the master of your kitchen. I mean, the problem with these big deep learning models that are trained on, YouTube data or even Hollywood data is, yeah, they know about a lot of different sounds of, different blenders, but nothing's as good as your kitchen. When you have a system like this that can live in your kitchen for weeks, months, years even, is it knows your kitchen like no other device on the planet, and it can be exceptionally accurate. So in the chat, I can see that someone asked, what happens if objects are moved around? It will tend to overfit based on the kind of reverb. and even the direction of arrival. And so there'll be a new calibration process where, hopefully a lot of the other features that it's generated correlate with that object, not just by the reverb. Hopefully the reverb even has some core, characteristics that maybe are similar. But again, it'll cluster it as a new cluster that's maybe somewhat different, maybe a slightly different location than the microwave. And then it'll do this confirmatory behavior. It says, is that still a microwave? And you're like, yes, that's still a microwave. And then it'll kind of add it into the existing cluster. So there's always going to be a little bit of refinement. But importantly, we want to make that user touch point really low. So you move it, and then 5 days later it says, is that still the microwave? And you say, yes. So it's really to try to minimize the intrusion on the user. Yeah, so if the smartwatch is moving around and you can't take advantage of things like the reverb, because obviously the room is changing, or like the direction of arrival, then it's going to have to rely on other features, and the deep learning will have to learn on other things. And fundamentally, toilets are always going to sound different than you opening a refrigerator, right? I mean, that'd be very weird if you made like a toilet sound, when you opened your refrigerator. So it basically just has to rely much more on the acoustic information. A cough sounds like a cough, a sneeze sounds like a sneeze, refrigerator sounds like a door opening, and so on. Being in your car, the inside of your car, if you want to have context awareness about is the person in a motor vehicle, actually the reverb and ambient noise inside of a car or a bus or a tram actually does sound quite distinctive. So this technique applies even when it's on the go. So let's actually talk more explicitly about being worn instead of being deployed, because obviously we want to have this. It's not like, even if you have a smart speaker sitting on your countertop, sure, it's the master of that domain, but fundamentally we're going to want to have smartness that moves with us in the world. So let me talk about some of those projects. So an early project was EM sense, so electromagnetic sensing here. And what we found, we took advantage of this very interesting effect, which is that pretty much any electrical object emits a little bit of electromagnetic radiation. Now that kind of sounds scary, but it's just interference. It's like a radio station. There's no, you're not gonna, you don't have to wear like any kind of tin hats or anything like that. Obviously in the United States, the kind of regulatory body for us is the FCC, and it very heavily regulates, what devices are allowed to emit. But fundamentally, anything that's using electricity and it has a motor, or it's switching, or it's using a touchscreen, anything like that, it has a little bit of electromagnetic noise that emanates out into the environment. You can think of it like a very weak radio station. It may not even leave the room. But what happens is when you touch an object that's using electricity, your body, when it couples with it, actually becomes an antenna for these signals. And so if we actually have a sensor placed on the skin, which in the case of a smartwatch we do, you can actually sense these little electromagnetic emissions, which are very characteristic of different objects. So in this case, it's a sander. So here you can see in this sort of demo reel on the laptop, I always like to show signals actually with a lot of my projects, because if you can see it, you can sort of believe it. So in this case, this is a frequency domain, so that you can think of this almost like an FFT. And you can see that as the user is going around and touching different things, we're seeing these different kind of spectral patterns of the EM emission. So something that's motor driven actually looks very different than something that's stepper motor driven, for example, or certainly something that's using a touch screen. And you can see on the laptop, again, just for illustration, real-time recognition. So, automobiles and motorcycles, obviously very noisy. They have a lot of, spark plugs and stuff like that, very noisy emissions. So this is a smartwatch. You can see there's kind of like wires hanging out of this prototype smartwatch, but this smartwatch actually knows what you are touching only when you touch it. If you're 2 millimeters away, it sees nothing. But the moment you touch an electrical object, it can recognize it. And it doesn't even have to be with your hands. There's one example in here of someone stepping on a scale. These are one of these electronic scales that also sense your BMI. And they do that by kind of sweeping through some frequencies to measure your kind of, fat to body tissue ratio. But that emits a signal that we can actually detect with a smartwatch that's on your hand. So what might you do with a smartwatch that recognizes what your hands are doing? So in this case, here's just a kind of a quick demo. Really, you can imagine, when you pick up your electric toothbrush, that the smartwatch, again, preemptively, you don't have to launch, the Sonicare app. It preemptively says, I know the user's washing their teeth. Let me, launch a 60-second timer for good hygiene. In this case, this was that scale again. And as soon as you step on, it automatically launches the app to show you, how many pounds you've put on, since the pandemic started, right? Just to remind you of how unhealthy, at least I have been. Here's, looking at patterns of activity. So the user touched the refrigerator, then they touch the stove. It's 8:30 in the morning. Maybe they're making breakfast. Do you want to, put on their favorite podcast or something like that? Here's, me touching my office door. It says, oh, the moment you're going to go into your office, let me just remind you that you have a meeting in 12 minutes and there's 12, important messages waiting for you. So you can imagine, again, sort of building these cues on. Again, you kind of open your office, think about, President Biden or, coming into his office. The staff are waiting there, ready to give him his schedule for the day, what's got to do, what's urgent, what's not urgent, and we're a long way from that future, but we're going to have at least the raw ingredients to open that up. Okay, here's another project, very similar. EM Sense was great, but it did require two things. One is we had to add on a new sensor to smartwatches, this thing that sensed EM radiation, but it also simultaneously couldn't detect non-electrical devices. So if you were using, scissors or chopping vegetables or mixing something, in the kitchen, they didn't use any electricity, so they didn't have any EM emission. So we said, well, how do we kind of plug that hole, expand our range of devices, kind of things that we could detect? So we looked at accelerometers. Accelerometers are found in all smartwatches today. And accelerometers, if you tune them right, actually can be used as vibration sensors as well. So here's actually an example of this. At the very top of this laptop screen is your typical 100 hertz accelerometer found in a smartwatch. And below it is what we've done to replace the kernel driver for the IMU. And now you can see it's much higher. It's 4,000 hertz instead of 100 hertz. And in this case, the oscillations of this toothbrush are easily seen. You can see that little sinusoidal oscillation of the motor running inside of there that you could never hope to capture with a 100 hertz accelerometer. It's way above Nyquist. And then, of course, there's a microphone as well on a lot of smartwatches, but that microphone is very susceptible to ambient noise. In this case, the toothbrush is kind of rattling on the surface, and the microphone still picks it up like it's held in the hand. But uniquely with an accelerometer worn on the wrist, in this case, a very high frequency accelerometer, is that it only detects that the user is using the toothbrush when you hold the toothbrush and it is on. So you'll see that sinusoid is present, and as soon as the user puts down the toothbrush, the sinusoid disappears. So again, it's very much like EM Sense that you have to be holding the thing and it has to be kind of running. So here again is just a demo reel. Again, I like to show demos. This is a rolling spectrogram this time of the vibroacoustics that are propagating through the arm. And this is an off-the-shelf smartwatch. This is not our own smartwatch. This is not a smartwatch we just bought like on Amazon. Replaced the kernel driver in the kernel for the IMU and just got the high-speed accelerometer data out of it. And now you can see on the laptop again, we can start to see an incredible range of objects. They're very distinctive. This is a single classifier, single model. And yet you'll see in these spectrograms that things are incredibly consistent. So here's just an example. You have a recipe maker. It says we want you to combine the eggs and mix it. And there's a progress bar here. But you don't have to, it doesn't say mix for 30 seconds. You have to set a timer. It just keeps track. And if you stop, the timer stops, right? This is like this little tiny aid just to help things out a little bit. We also found that you could, for example, tune a guitar by actually looking at the vibrations that are propagating through your body when you're holding the kind of tuning knobs for the frets. So you can actually see on the smartwatch there, it's telling you to tune up or down. So this is just an example of the kind of bioacoustics transmitting through your fingertips. Pretty amazing. So here's another example of just a toy, little kind of crossbow here. And the smartwatch is just adding this kind of like passive app. So it's kind of keeping track of the number of darts that you've thrown. It knows when you reload, it's a very different vibroacoustic signal. And it says, you've got one little dart left to go. And you can imagine sort of almost providing like an augmented reality kind of experience through those. So we followed this up. We said, okay, that's cool. So now when we have objects, like a drill or, a toothbrush or, whatever, blending something together, anything that produces vibrations, we can try to detect those too, in addition to electromagnetic emissions. So now we're starting to cover a good range of objects, but there's still a lot of things that your hands get up to that are not included in that, like combing your hair. That doesn't really produce vibrations. They're not these kind of periodic things, scrolling on a touchscreen, using a mouse, things like that, washing your hands, right? And so we kind of doubled down on this approach using the accelerometer. We attacked this problem again, but this time we wanted to look at what we called hand activities. So things that, again, same like activities like playing a game of football or rugby or something like that. You can also imagine your hands get up to activities as well. And so to collect data, we actually deployed, we had 50 users wear our thing for 100 days of total deployment. So we collected about 1,000 worn hours of data. And we did experience sampling for those of you who are familiar with that technique, where the smartwatch would mostly be off, but in a random period around 15 minutes, it would wake up, it'd wake up the thread, it'd start to record all of the IMU data, then the screen would wake up and it would vibrate and say, what were your hands doing 2 seconds ago? And the user would say, oh, I was writing a note to myself, or I was eating lunch, and they would label it. There was a big long list, and there was a companion smartphone app, so they could also type in things that weren't in a list. So we got this 1,000 hours of data about what do hands get up to. And unsurprisingly, if you look at this kind of rank ordering here, almost 1,800 of our 5,000 samples are just the hands still. So many of you are probably sitting there watching this presentation. Maybe some of you are surfing around on Facebook, but for a lot of the time, our hands are still. But other times, people are typing on keyboards, scrolling on trackpads, all the way down to smoking and dancing and in the shower and so on. And we had data to look at this, and we focused on activities that we thought were particularly interesting and tractable. And so here again are some of the spectrograms for these different activities. It's a little hard to see here over short periods of time. What characterizes an activity over sort of like an instantaneous action is that there has to be a duration, right? When you clap, you don't clap once, like that'd be kind of disturbing if someone has clapped a single clap. Clapping is the notion of this sustained activity. Same with sort of operating a drill, or drinking or brushing one's teeth. You don't do it for 500 milliseconds. It tends to be something that lasts at least 5 seconds, and we need that to build up enough confidence to do that. So these are the 25 activities that we selected to study. And here's just again just a little demo reel of the real-time classification happening, and this is actually using much lower sample rate accelerometer. So we can see here it takes kind of a couple seconds to stabilize. So we don't do any. This is the raw classification here. We actually use a voting window in reality, and you can see that after you kind of get moving, it does recognize things pretty well. So it knows that when you're writing with an implement, it knows when you're, for example, cutting out something with some scissors. Again, it takes a second to stabilize, but then it gets pretty confident in what you're doing. And one thing that we looked at in particular was kind of a kitchen activities, domestic activities like washing dishes and washing hands. And one of the cool things that came out of this research was Gerard Lapote, who you can sort of see, just his lower body here, as he went off to, after he graduated his PhD from my lab, he started a research group at Apple, and he was able to squeeze down a future derivative of that model to actually enable hand washing detection, which is now a feature on Apple Watches. So if you have an Apple Watch, or at least a recent Apple Watch, you may have noticed that in WWDC 2020, Apple released a hand washing detection feature that when it detects that you're washing your hands, it starts a timer for 20 seconds to help combat the spread of COVID-19. So it actually is an example of research trickling down into a product, and kudos to Gerard and his team for actually being able to ship a feature like that. Okay, so we've talked a lot about input. There's a lot of other projects in this space that my lab has done, even some newer projects that I didn't include here. So if you're interested in this sort of thread of kind of ubiquitous computing, sensing, general purpose sensing, definitely follow up with me by email or visit my website. A lot of projects there done by the brilliant PhD students that I have. I can't claim 100% credit for all this research, but I want to switch gears a little bit just to round out the presentation, given that we have about 10 minutes left before we move on to questions. So we've talked a lot about input, but what about smarter output, right? Like, so great, you've convinced me that we're slowly working towards this idea of smarter contextual awareness, but how do you express that smartness beyond just the kind of rudimentary methods that we have today? So let me just give you a little bit of a flavor of what my lab has been doing on that space today. So this is the state of the art for the smart light bulb. As we sort of alluded to in my presentation title, I'm not particularly enamored with this notion of smart, because we apply smartness in kind of very egregious ways. A smart refrigerator is really just a refrigerator with like an Alexa built in or something, or maybe it has a touchscreen, but really it's just like someone took a tablet and stuck it in a refrigerator. Does that really make it a smart refrigerator? Does that mean the refrigerator does a better job at refrigerating? And in most cases, not. Like the example that I really like to harp on is a smart toaster. There actually are smart toasters out there, but they're smart in that they've been given wireless connectivity. So they're Wi-Fi connected for reasons that are not entirely known to me. And often they have a voice agent in them. And sometimes they can be done programmatically. So for example, the killer application for the smart toaster, besides just having a smart speaker integrated into it, which seems somewhat gratuitous, is that you can put the bread in the night before, then you can go to bed. Then 8 hours later when you wake up, you can say, hey, Alexa, make me toast. Of course, by that point, your toast has gone totally stale, but it can make your toast for you without having to get out of bed. How that makes it a better toaster, I don't really know. What would be an actual smart toaster would be a toaster that makes better toast. that somehow uses machine learning to maybe cook my toast faster, and it's more delicious because it's doing a little bit of smart sensing on what type of bread I put in. Is it day-old bread? Is it new bread? Is it challah? Is it a baguette? Or is it a bagel, right? Those, you don't just like dial it up to 10 and toast it. Those all need to be toasted different ways if it's going to be an exceptionally smart and good toaster. In the same way, like a chef doesn't always cook lamb and chicken and beef exactly the same way. That'd be a very weird way to be a chef. So I think the smart toaster is actually a real thing, but actually no one's really made it yet. And I think that's sort of true with this smart light bulb example as well. Basically, our smart light bulbs are ones that change color. That is the pinnacle of light bulb technology. Maybe there's one, there is also ones with a smart speaker built in. Just because you put a smart speaker in a thing does not make it, smart, in my opinion. I personally think that Thomas Edison would be extremely disappointed. It's been more than 130 years since we invented essentially the modern he invented, incandescent and electric lighting. And in the 130 years, we're still using the same base. Amazing. That's called the Edison base, at least here in the United States. But all we've been able to do in 130 years is allow them to change color, but we haven't really made them any better. I think that's incredibly disappointed, and Edison's probably turning in his grave. So we can ask ourselves as HCI researchers, what would be a smarter light bulb? What would be, how do you make light smarter? And I think it's probably going to involve projection. So here's an old project I did. I've been looking at this domain for a very long time. And I know people like Professor Billinghurst have been looking at it even longer than I have. But how do you actually kind of embed computation and interactivity into environments? And so I think the way to do it, or at least one way to do it in an elegant way, is with projection. So this is a project called WorldKit. And it's basically a way to paint sensors onto your world: buttons, contact sensors, multi-touch, whatever you want. So here's an example. This is one of my other students, Robert Chow, again, graduated now, a professor at University of British Columbia. And he has an app for setting an away message that's displayed on the outside of the door. And in order to generate the interactors, he's literally painting the widgets onto his office. So there's a projector on the ceiling here, and he's literally painted a custom interface onto his world with his hand. And now the world is essentially, buttoned and is basically like a touchscreen. Now, here's what that hardware looked like in 2013. So, this is 8 years old. It literally is a first generation Microsoft Kinect hot glued to a digital projector. There's nothing fancy here. And we just like stuck it up on a piece of plywood on a tripod. But over the years, we've been able to enhance that. So, a couple years later, after a long series of things, we're basically able to miniaturize it, not really by work of our own, but just because of the advance of companies like Intel and Apple and Samsung and so on, just the making miniature projectors and depth cameras and small computers and so on. And this is actually what we have today. This is actually a year and a half old, but this is our latest generation bulb. You'll see it now has that standard Edison screw fixture for light bulbs, and that's because it fits standard sockets. You can go to a light fixture and screw it in. And it is sort of floodlight size, so we're not kind of gotten it down to regular light bulb size, but we're getting pretty close. And this inside of this has a power supply to go from AC power to DC. It has a computer in there, quite a decent one, multi core graph GPU and so on. It has a projector, and it has a depth camera for touch sensing. And the idea is you take this, you go to your hardware store and you buy a 6-pack of these bulbs. They're essentially Android computers, but with projectors and depth cameras instead of a touchscreen installed. And if you have a desk, you can unscrew your hopefully LED bulb, and you can screw in one of our bulbs, and now your desk is a computer. It becomes a computer. Same with your kitchen. You might have recessed can lights above your kitchen. You can unscrew those, screw in 1 or 2 above your kitchen, and now your countertop is interactive. And here's what the latest generation of our software looks like. The green dots are debug for our touch, so don't worry about that. It's showing kind of hover and touch. But the important thing here is that we have a full multi-touch interface on the world, and we can actually snap to things. So in this case, it's highlighting snap points, so I can actually attach a number keypad to my laptop. All of this is responsive layout. These are essentially web applications being rendered as textures that are texture mapped onto the world. But I can have a calendar app that I can put anywhere. I can snap it to the corner of my desk. I can snap it somewhere else. You do have this problem that, obviously you don't want to be able to put your coffee mug down onto that number keypad and it starts, typing input into your laptop. So we need to be able to run away from, from physical objects, but not run away from your hands. And so we need machine learning to basically tell hands apart from other things. But fundamentally, these are just multi-touch apps. In the kind of ultimate embodiment of this, any application that's on the Play Store or the Apple App Store, this could run on your world. Because what we're doing to these apps don't know they're running on this IKEA table, or that they're running on your kitchen countertop, or they're running on your wall or your coffee table, whatever. It doesn't matter to the projector. It doesn't care. It makes no assumptions about the environment geometry. Obviously, it has to be not glass. A glass countertop's not going to work, or glass, coffee table's not going to work, and it can't be too dark. But even a wood kind of thing, it actually works pretty well. But essentially, all of those apps that are already written, that are meant, and most of them have responsive layouts. They can run on tablets and phones and so on. All those apps can run on this device instantly. You don't even have to recompile them. They're literally just Android APKs that you can run on the world. So this is not going to require developers to do anything. The Gmail app can now run on your table. The Twitter app, can run on your wall, whatever you might be. So I think, we're not there yet. Maybe next year, maybe the year after, but we are tantalizingly close to actually being able to do this. That device that my lab made, it's a reasonable approximation, but it isn't the fit and finish that you'd want for a consumer project. In particular, the cost is still pretty high. That our light bulb costs around $500, maybe $1,000. But economies of scale, you could get that down to essentially what a cheap Android smartphone costs, and those can be under 20 bucks, 20 USD today. But we are still working with OEMs to make that future possible. So we teamed up with a company called ASU, and they were really experts in very small projectors. And we worked with them on this collaboration. So what you're seeing here is actually an entire computer. This is a quad-core Qualcomm processor, not the fastest thing because there's some thermal constraints here, but you can see the specs are pretty reasonable. And there's also this little tiny depth sensing array. And we were able to, this is the entire projector right here. This is about, here's a centimeter. So this is a couple coins across, but this is a full RGB micro projector, full on computer. And we actually exceeded our design goals of making a light bulb. And we said, well, hey, this is so, so small. Why don't we actually just go right to, a really, really tough form factor, which is a smartwatch. So here is that smartwatch form factor. And we're actually doing oblique projections. So we have to do some kind of clever texture mapping to actually get this work. But you can see we're actually able to do even, touch tracking on the skin, but obviously a table would be even easier. So I think we're actually kind of all the technologies are really close to being done. And I can't really say too much, but we actually are working with some OEMs to be able to actually bring this to reality, but at a cost that I think is that you could go out and buy a couple of these for your house. You wouldn't go out and buy, if they were $1,000 each, you're not going to be going to a hardware store and buying a 6-pack anytime soon. Okay, so just to wrap up, because I want to save time for questions, and I can see that Samantha has a question, and I haven't ignored you. We'll get to that in a second. So let me just wrap up sort of this arc. Again, I like to think about history, and I think everyone should really think about history, because extrapolation is a really powerful thing. So let's talk about, again, going back to kind of my core topic, which is about computers having knowledge, okay? What is the historical trend of computers knowing about the world around them? So if we go all the way back to the kind of original advent of electronic computing, 1940s, 1950s, computers knew nothing about the outside world, right? They had very limited memory, on punch card or on tape. That was whatever you put into their memory was all they knew. They didn't know anything about the weather. They didn't know anything about the room. They didn't know they were a computer. They just knew what was loaded into memory, artillery range tables for the most part in the 40s. Now, when you get into the 1960s and 70s, now knowledge starts to expand, right? We start to have sort of proto internet-like things like the ARPANET, and we start to actually have a drive to start to digitize the world, okay? So probably seminal among these is SAGE. This was a US strategic air defense system for tracking planes and ICBMs coming into US airspace. And that was a very deliberate attempt to say, well, hey, computers are amazing tools, but why do we want to digitize things in the real world, not just crunch on numbers in their own memory? So it needed to tie together radar stations and information into a central thing. But it was the first time really that computers knew about the outside world, or at least some dimension of it. And into the 80s and the 90s, now we have this explosion of knowledge. So number one, we're, weather and weather satellites, weather radar, Doppler radar. That's a great source of data. People want to know about weather. We want our computers to be able to tell us the weather. And so we've added that, and it became ubiquitous in the 90s. And then with things like kind of Google Maps, we start to get actually real-time traffic, not just historical traffic, but real-time traffic by around the mid 2000s. But in general, knowledge has expanded to anything on the World Wide Web. I can ask my smartphone, tell me the entire history of Auckland, because it can access all that information on the World Wide Web. So the purview of computers expands dramatically in the 80s and 90s. And then in the 2000s, and really until the modern time, kind of the advent of IoT and Wi-Fi and these little sensor boards has let us digitize everything, right? So we have smart thermostats, we have wired smoke alarm systems, and so on. fundamentally, if you were to build a new building in, today, like a new building on campus, it would have electronic controls for the fire alarm system. It'd have electronic controls for occupancy, for lighting. It'd have it for HVAC. It'd have it for the elevator bag. All of these, even though they may not be exposed on the internet, fundamentally, they're all network technologies. They've chosen not to expose it to the World Wide Web because it doesn't have to be, or maybe for security or privacy reasons. But fundamentally, all of these systems are digital and networked, and those are able to be taken advantage of by smart building systems. So there's been an incredible expansion of highly local knowledge, not just what's on Wikipedia or what the weather is like in Pittsburgh, but really what your local environment is. We've got them there, but we're not really utilizing it very effectively. But what I want to kind of impress on you is that I think if you really kind of plot this out, obviously this is very unitless and messy, but I think what we actually see here, if you really kind of were to do a careful study of it, is that it's actually exponential. And that's a really important thing to understand. And actually, Scott Hudson has a great talk from last Chi. He got a Lifetime Achievement Award, and he talks about how HCI people get exponentials wrong, or really everyone get exponentials wrong. Exponentials is not a correlation or a behavior that humans are good at. But in the same way, it was really hard to predict. No one could really believe that Moore's law would kind of continue. But think about this. What an exponential essentially means is that in the next 10 years, we're going to onboard into computers' purview, whether that's the internet or internet plus plus or metaverse, whatever. But in the next 10 years, we're going to add more knowledge, more facets about the world than all of the history of computing back to the 1940s. So like, if you think, wow, look how much IoT we've deployed in just the last 5 or 10 years, that is going to be a mere fraction of what we're going to see in the next 10 years, in my opinion, because I think this exponential is going to hold true for quite some time. So it looks like, wow, everything's online, but actually it's not. Think about in your house. When you build a house, is everything really digitized? Is your rice cooker digitized? Is your blender? Is your toaster? All those are waiting to jump onto the internet. And that, I think, will be the next frontier. And when all those things are connected and computers have ready access to all those kind of facets of your existence, and they can say, they're making dinner, they're making an important dinner, this person's on a first date, whatever the important thing might be, that's going to be a real game changer with some really important implications to society at large as well. So just to wrap up, I think we're at what might be described as sort of level 1 context awareness, or we're very, very close at least. And this is where our smart devices, like the next generation Alexa, next generation HomePod, next generation smartwatch, is probably going to be able to answer rudimentary questions like this. Is my laundry done? If you ask right now to like a Google, smart speaker, is my laundry done? It'll be like, I can't help you with that, but here are some search results, or here's the definition of laundry. Absolutely not smart. But I think we're really right at the cusp within the next, certainly, year or two, that we're starting to get to this thing. And this is already a very important step towards enabling this kind of context awareness, and much more like a human assistant. They're starting to become more like assistants, and maybe a little bit like coherent partners. But this is a research trend that's going to take probably the rest of my career. So on that note, I will finish. I'm happy to take questions. Obviously, I should acknowledge all of the incredible PhD students. These are the 6 PhD students that have either graduated or in my lab, and everything you saw today was done by their incredible talent. So thank you for coming and paying attention, and I'll stop sharing and take questions.
Thank you very much, Chris. That's a very inspiring talk, and I'm sure we have lots of questions.
So maybe I can actually jump back to Samantha, since I ignored her for a very long time, if that's okay.
Yes, please.
So I saw this question pop up when we were still talking about some of the smartwatch projects. And yes, power consumption is a major issue. In most of the papers, we do document what the smartwatch consumption, or sorry, what the power consumption is like and its implications for a smartwatch. But it actually can be done. And actually, Gerard showed it by actually shipping a commercial feature, which is the hand washing detection. That is running all day long on your Apple Watch, if you have an Apple Watch, and it shows that it can be done. Obviously, that's a single class, but the power of mobile computing is still following essentially Moore's law. Moore's law is maybe coming to an end in sort of desktop and server class computers, but in the embedded space, the Arduino space, the kind of small microcontroller space, smartwatch space, it's still essentially following Moore's law, especially with dedicated hardware for things like neural computation. And so actually the power consumption is very modest on those devices. You can have, wake word, on your smartphone. A lot of smartphones have a dedicated, essentially coprocessor or ASIC for listening for things like, hey, Google. And that's running all the time, listening all the time, running the microphone all the time. And it'll wake up and wake the main application processor up to be able to process that. And they can actually get down to microwatt power consumption, which is absolutely an incredible feat of engineering. So it's not that it's an easy problem. I don't want to give that impression, but actually, the state of the art is already able to run these processes continuously. Okay, moving to Amit. He says, have you tried accounting for microphone directivity patterns, different microphone types for the ubiacoustic projects? Have you found this doesn't really matter? Have you tried training your models or simply rolling off highs and lows for the samples you just simulate distance and fall offs? I mean, certainly when we train our deep learning models, one of the parameters we vary, in addition to things like reverb and background noise, is amplitude to account for sounds happening at different distances. So that's sort of tied in among many. We even change the pitch of things as well as another manipulation. So how your doorbell sounds, how my doorbell sounds, can vary by pitch and intonation and tune and so on. In terms of kind of the microphone, patterns like cardioid, et cetera, it really just omnidirectional is what we've always used, because you never know where sounds are going to come from. Even sometimes if it's like a smart speaker against a tile backsplash, you get very characteristic multipath off that backsplash. And so fundamentally an omnidirectional microphone is still pretty useful. But we haven't run a study that looks at these different patterns, so it may be useful. I suppose it's an open question, but my kind of gut feeling is omnidirectional is probably a good way to go. Okay, so those are 2 questions in the chat. Does anyone have any questions they want? Okay, so
we have a question from Professor Suranga, if you'd like to start.
Hi, Chris. That was really wonderful. And we as a lab get a lot of inspiration from your work, and we admire your work. So that's really great to see you giving this talk live. I have 2 questions. One is a question that I get asked and I don't have a good answer. Second is a question on behalf of a lot of early career HCI researchers. The first one is about, with these wearables and how we integrate them and making them, as you said, being a collaborative partner. We get a lot of assistance that sort of increased in our capabilities, enhancing what we could do. I often get asked, where do we draw the line? Where should this stop of enhancing, augmenting ourselves and increasing our skills? Who decides that, and where should this stop, and where's the line? And I don't have a good answer for that. That's number one. Number two is, especially when we present to non-HCI groups, oftentimes we get asked questions related to what's the science behind, did you guys integrate existing technologies to show a new possibility? Is that really science? What I used to do is I was leveraging on Jacob Webb-Brooks' paper on HCI contributions. I was trying to link to what we do into those 7 categories. I don't know if you have a better answer for the early career researchers when they get presented to non-HCI crowd, and how do you get them to appreciate the science behind what they do?
Yeah. Okay. So let's go to both of those are pretty whopper questions. So I'll try to be efficient here. So, is there a line? Is there a line where there's too much augmentation, or that it's actually becoming intrusive? Do we even want smartwatches, or do we want this notion of computers as partners? And there is no one line. There's no like, oh, we want to stop at this line. I mean, I don't wear a smartwatch, and even though I research smartwatches, so clearly, I'm like in the Stone Ages compared to many of you. I think what's important to realize is that market forces are going to decide the success of things, right? It's really hard to predict, and consumers will vote with their money. Where Google Glass might have been a failure, maybe someone's going to, Apple might release an augmented reality headset and it's going to be an overwhelming success, or it'll be another failure. It's really hard to know because there's a lot of societal factors here about perception. And I think a lot of people don't want to be augmented and don't want that future. There's something nice about having a hammer that's only a tool. I don't want to pick up my hammer and it's morphed itself into a screwdriver. And I'm like, no, I want, a hammer. There can be frustration there as well. So I think what I view this problem as is we should innovate. We should try to come up with that notion, explore what that future might feel like. And through, the power of video and exploration and, what HCI is good at, is see what people's reaction is. If everyone watching this presentation said, everything I saw today, I don't want any of it. Well, that's really good feedback. That really says something, because hopefully I'm not embarrassing anyone, but this is probably a pretty nerdy audience, myself included. If we don't find this interesting, then who should we expect to, find this compelling? So we are sort of our own kind of, we should kind of dog food these things that are ourselves. But fundamentally, I think the job of an HCI researcher is to explore those probable or possible futures, not even probable, but explore those speculative futures to see, is there something interesting there? And more importantly, is ask difficult questions, which so far no one's brought up, but what are the privacy implications? How do we get ahead of the ball? We don't want Facebook to ship it, and then we find out 10 years from now, oh my gosh, it was a disaster in privacy. We want to bring those kind of questions to the forefront now, so we as researchers, as stewards of the community at the forefront, can ask those kind of questions. So I think it's more about exploration. It isn't about, let's ship this commercially right now. For COVID, yeah, great. Hand washing detection has probably saved, some lives, tens of lives. I don't know. I'm sure Apple has run the computation about how many lives that's saved. Fantastic, but that's not going to be true for most of these technologies. To speak to the second half of your question about, where's the science in this? You're right. It is sometimes science-like. I think a lot of what I do is more invention than science. But I would say that HCI contributions and science in HCI can be two things, right? There's discovery, where you're unveiling, a new truth about the universe, like you've discovered gravity or how some genetic, sequence works. And there's invention of a new thing. That it's not like a self-evident truth about the universe. It's like I've just invented some new thing. It's sort of like art. I've created a new artifact. Both of those have tremendous value. I think where the science comes in, so I mostly do invention. I don't do discovery. A lot of social computing researchers, or certainly people on the behavioral side or learning science, they're really doing discovery-based research, and that's great. Medicine, right, is really a lot of discovery-based research. I do mostly invention, but where the science comes in is how do you vet and verify that you're doing those things well? All of my research has studies, has experiments, understands the physics of electromagnetic propagation in the body, the propagation of bioacoustics in the body. You have to deeply understand the science to get it to be effective. Otherwise, your technique doesn't really work. It's just science fiction at that point. But the reason why I like to show the signals in my talk is because, again, people can see, oh, that looks like that and that looks like that. That looks pretty good. But I think in order to get to that level of fidelity, you have to understand the physics and the chemistry and the anatomy of people, of the world, right? And so that's where the science comes in, is that our contribution may not be science per se. I think it's the invention, but science is that glue that underpins quality research, and the scientific method is how we go about attacking, realizing those inventions. So I think science is really core to what we do, even if you can't say, hey, that's a Nature paper right there. They've, here's this, scientific principle that they've uncovered. I think it's like, same with machine learning. I'm not a machine learning researcher, but that doesn't mean I can't apply machine learning in very powerful ways to advance humanity in my research. I think the same about science. I'm not advancing the practice of science, but I use science in my research all the time to make it better research. And I think that's totally fine. I don't see that as disingenuous or bad.
Thank you. That's
Thank you so
great
much.
question. Sorry, Saranga, did you have anything to add?
No, I said this is really very useful way, especially for many of our PhD students and postdocs joined in this meeting. When similar questions get asked on your work, this is very useful to think about. So thank you so much for that answer.
I hope my answer was satisfactory. I mean, that's just my opinion. You'll hear a million different opinions on this. It's a controversial.
Yeah, so that's exactly why I asked, because I mean, as HCI researchers, we often value, and there's no question about the value of your work. It's more about sometimes we get asked the kind of question that I ask from other people who are not in the field when we have to present to groups outside HCI, and then it's a harder deal to justify, and you gave a different perspective for us to articulate. So that's why I was trying to pick your brain on that.
Okay, glad to hear it. Aladdin, I don't know if you've been tracking who raised their hand first.
Yes, so Samita is next.
Okay.
Thank you, Aldi. It's a great presentation. Thank you for that. And as Suranga said, your work is a great inspiration for all of us in our lab. And my question is like, in your context sensing approaches, in my point of view, I mainly understood two categories. One is on-body context sensing, and the second one is kind of detached from your body, it's kind of like attach a sensor to the environment and sensing. So going further, do you think what is most acceptable by the people? Is it on-body sensing, or is it that detached from your body, or is it a combination of it? I saw that you have already implemented some of the sensors in a university building. I'm really curious about the acceptance of the people, whether people more accepted the on-body sensing or the sensing that detached from the body. Yeah, that's the question. Thank you.
It's a good question. I mean, we've explored both because we don't really know. And I don't think I really have a great answer for you. I think they are different tools for different purposes. I think the nice thing about having something that goes with you is that you get that smartness everywhere you go, right? I wanted to know the moment I turn on my car to go home at the end of the day, and it should automatically pop up, hey, don't take this street because it's closed for construction or there was an accident, right? It should just prompt me automatically. There's no point that being on my smart speaker in my office. I need to know that the moment I'm starting to drive home. But when I'm in home, and again, smartwatches are essentially maybe glasses in the future, assuming that everyone wants to wear glasses. Maybe that's essentially like having a smart speaker everywhere you go. But for now, I mean, again, I'm not someone who wears a smartwatch, is I'm okay with the smart speaker being the sort of hub of interactivity in their environment, so that my office speaker really knows my office environment, well, and even knows how I speak. I mean, how I presented this lecture or this presentation, that's not how I speak with my wife, right? I'm like, if there was a smart speaker that only lived in my office, they probably know this is Chris Harrison's voice when he's talking with a student in his class or when he's talking with a colleague. And that's probably different from how I talk at home or with my mom, right? And so that kind of nuance has to happen in those respective environments. That's a little harder for maybe a smartwatch to figure out. I mean, I guess you do geolocation and so on. But anyway, long answer short, I think there's value in both things. If we want to move these technologies out of just pure research and into the world, we should embody these technologies in anything. And honestly, from the standpoint of the machine learning or the deep learning, it doesn't care if it's in a smart speaker or in a smartwatch. It's just a computer with a microphone. They're all basically the same thing, right? So they can go in your TV, they can go in your laptop, they can go in, your future smart toaster, right? It doesn't really matter from the standpoint. I do think what is important though, and what's nice about something like a smartwatch or a phone, is by virtue of it going with you, it is clearly your personal property. I think where it gets a little bit dangerous is if you walk into someone else's office or into someone else's home, that smart speaker is clearly theirs. You might be wearing your smartwatch, but that smart speaker is theirs. And it's essentially processing you, recording you, learning what you sound like, right? If it's like listening and learning. Are you okay with that? Do you have to opt out of that? Is that their data? Do they own that data now? That's when you start getting into some tricky issues. So I do think kind of sensors that are clearly yours, like a smartwatch that are coupled to your body, has some less kind of tricky privacy issues in some dimensions. I forget what your second question was. What was the second question?
It's actually like the second question is like, what do you think that the most accepted way in future? In a way, you already answered that question as well.
Okay. Yeah. Okay. Good.
Thank you so much.
And next, we have a question from Ishan.
Thank you so much, Chris, for your presentations. They're very awesome. Looking at your presentation, I'm just wondering, because in your presentations, we detect input as well as giving like smart output. I'm wondering, did you explore the emotion of the user itself? Because I think this is one of interesting thing with the technology can inform how we can interact better with the technology itself or with our surrounding, because knowing the context of the emotion or the situations of the user, I think is very important. I just want to know whether did you explore this kind of area, and then how do you see exploration in this kind of field later on? Thanks.
So number one is I 100% agree with you. Emotion of the user or affect of the user is enormously important. And again, this is what makes a human assistant so good. If they see you come home from, your studies and you're frustrated or you're upset, they're not going to come and say, here's a piece of junk mail you have to read right now, or call you on your phone with some ridiculous telemarketer, right? They obviously are taking that into context. Or if you humans are great at reading this. Now you pass a colleague's door and their door is cracked, so you can sort of see in their office, and you see them crunched over, a laptop frantically writing emails. You're not going to knock on the door and say, hey, how's it going? Let me tell you about my weekend, right? It's like humans are just really good at this, and that's what makes kind of human-human communication very powerful. And computers, they don't care at all. Your smartphone will ring, doesn't matter if you're having a good day, bad day, in the middle of a final exam, no knowledge at all. So I 100% agree with you. But the other answer is no, it's not something that I study. This is something that other researchers in HCI study extensively. They're doing it with biosensing, from things like a smartwatch. Obviously, a great thing about a smartwatch is that it's living on your body. It can sense things like galvanic skin response. It can look at blood pressure, heart rate, and so on to infer activity or infer emotion rather. Obviously, computer vision studying your facial affect. Are you smiling? Are you frowning? So there's a lot of research going on in that domain. And absolutely, when we think about this notion of sort of general purpose sensing and building up these kind of meta sensors, emotion, affect of the user is going to be a huge part of making those sensors like, is this a good time to interrupt someone, right? There's no sensor for interruptibility, but obviously the affect of the user is going to be an important building block, one of many things that have to feed into that. So yeah, it's a really interesting area of research. I just happen not to research it, but it's fundamentally important to the vision that I sort of laid out.
Thank you, Chris.
Thank you. Next, we have a question from Moritz.
Yeah, thanks, Aline. Thanks, Chris, for your awesome presentation. Also picking up the comments on the fly. I felt like it made it really interactive. I think we touched my question already indirectly, but I just want to ask you, you gave us the perspective of user agents in the future, specifically that make use of being aware of our context. And I think you pictured a future people would want, at least I would want it. And you said the technology is basically ready now. So what, in your personal opinion, are the main challenges? Why is it not out there at the moment? Is it the user acceptance, which we already touched, or is there something else in your opinion? Thanks.
So I think user acceptance is certainly part of it. Although people are, buying smart light bulbs and are perfectly happy. People are buying, smart refrigerators and, using them as iPads stuck on refrigerators. So I think there actually is a hunger there. If you really had something that you're like, whoa, like I knew it was in a rush and it just decided to make toast twice as fast because it knew I'm heading out the door, right? It somehow like just inferred, let's make rapid toast today, right? So I think there is an opening. I think, and when I say we're getting there, I think we're sort of getting to that very basic, like, hey, Google, has my mail arrived? And it's like, yes, right? Or is there has UPS left a package outside my home? Yes. That's like very basic, like computer vision or, basic sensors. But that notion of like, I'm in a rush to head out the door, I'm frantically working on submitting an assignment, don't interrupt me, that we're still quite away from. And I think what we really need is much more sophisticated models, probably deep learning or something of that ilk to really build these sophisticated semantic understandings of people. But what I really try to argue in the talk is that it's really hard to expect that of computers when they have no inputs, right? Like, yay, GPS on phones was a huge boon. It enabled things like Uber, right? Like just the addition of a GPS geolocation, which is a very coarse but highly useful piece of contextual information. Like, where are you? We can change the behavior. But we haven't really added anything to that, list of ingredients to make computers even smarter. So I'm wondering, what does it mean if computers know your pose, know your activity? Is there like whole new apps like Uber that just magically open because we've given these devices so much more knowledge? Again, a smartwatch knows nothing about your hands. So what are the apps if it knew what your hands are doing, that you're making dinner? Does it pop up recipes? Do you want to buy, I think you're making eggs, scrambled eggs this morning for 99 cents. Do you want to download like super scrambled eggs? And it's like popping up ads or something right on them. So I think we need to think more about that. But I think fundamentally, deep learning has come a long way. And I do think probably the low-lying sensor inputs is really lacking. It's hard to kind of build your fire without any of the kindling. So that's why I sort of advocate this bottom-up approach. Like IoT's been around for a while, but like I'm not in a smart home. Like I would love it. But the problem is, again, like if you want to buy that smart refrigerator or that smart toaster, which I nominally advocate, it goes from being like a $15 toaster to a $150 toaster, and it's not actually smart in the way that I want to. So why would I buy it? So the ecosystem is sort of broken, and there's very much like a chicken and egg. But actually, now you make me think about it. I almost feel like the deep learning is tantalizingly close, but we're kind of not giving it any of the fuel to do anything really sophisticated with context. but it's a very multifaceted problem. So that's a simplistic answer to something that's going to take, the better part of 10 to 20 years. You'll be an old man before the time you actually see this probably come to fruition.
Thanks so much.
Thank you. Next, we have a question from Tarindo.
Yeah, thanks, Aladdin. Thanks, Chris, for the nice talk. And I'm really into this kind of stuff. Like I personally believe that I want to make everything smart around me. So this is a very personal topic for me as well. So I have a question around the sensing part that you did, where you had a bunch of sensors collected in a board and you plug it and you sense everything. And you said that you got rid of the camera part because of the privacy issues and acceptance. So what is my question is, how is audio different from video? Let's say if my phone is now continuously listening to me for my wake word, and that means its microphone is on 24/7 and it's listening to all my conversations, whatever I'm talking with anyone. How is it different from audio and video? Why video is more privacy concerning but not audio?
Yeah, so what I advocate is same with video. So the reason why we didn't include the camera is when people see a camera, like it's almost like an icon for like, whoa, that thing is like potentially filming me. That's why people, probably people in this room put like a little piece of, tape over their camera. How many people do that? Raise your hand just in video. Does anyone have like tape over their thing? Yeah, people aren't taping over their microphones, okay? Or they could, but they don't. So cameras are like a very special breed of sensor that really, people get kind of worried about. But more importantly, even if you have a camera, but certainly with a microphone, I advocate doing all of the processing locally. So that's why I really say kind of acoustic sensor is in that project, there's never any audio leaving the device. So there is a microphone sensor, but right there, as soon as it gets past the ADC, is we immediately featureize it and denature it. So there's no like WAV of like your audio conversation, because I agree. An audio recording can be just as bad, or if not worse, right, than a video recording, where you're trash talking some, colleague and he's listening in the other room. That's going to be bad news, right? So the way around this, I think that's actually, we've looked at some really weird sensor data, and like, you'd be surprised what even just like a humidity sensor, like why is there humidity spiking at 2 in?" And I'll let you imagine what might be going on to do that. That's privacy invasive too, even something that says barometer, or humidity, right? So I think you should, privacy lies across a spectrum, and you should always, I think, do your best to denature it in a way that lets you recognize activities, but doesn't, really have something that's incredibly damaged. Like the threshold I think about is if that data were to leak online, would it de-anonymize me? And if it did, would I be embarrassed by it? So obviously audio recordings, if it is like everything I've ever said just gets published online, I probably would be embarrassed. Video, yeah, like me walking around in my underpants, I'm sure that'd be embarrassing. But if like my barometer data leaked online, would you even know it's me? Probably not. Even if you knew it's me, would there be anything really embarrassing in that barometric data or compass data? Probably not. So what I think the rule should be is that even if your audio data leaked, researchers and everyone can tear through it, and they really shouldn't be anything embarrassing. Yeah, maybe they'll know I was talking in my sleep or something, one night, or they might know that something was happening in terms of activity. But am I going to be horribly embarrassed by it? Hopefully not. And I think that's a good bar. That basically it should just assume, from a security researcher perspective, right? There's no such thing as a 100% secure system. So basically, you should just plan that data is going to get hacked. So then, how do you make that data as privacy preserving as possible? And I definitely advocate everything being done on edge. I think this whole smart speaker notion of let's just record and ship it to the cloud, ship it to Google, ship it to Amazon, I think that's not actually a technical problem anymore. I think it's laziness, and I think it's actually kind of malicious. They want that data. That's why they do it. There's no excuse in 2021 why that couldn't happen locally. The voice recognition models, activity recognition models, that can all happen on device. And Apple, for their hand washing detection, that's all happening locally. That never streams out of the device. That's all on board. So I really think that that's the way we should go.
Thanks, Chris.
Thank you. I have one question. I know we are reaching the end of the time, but you touched a little bit about smart output. And the example you gave is about the projector style or the visual kind of output. My question is, are there a different kind of output you think can be smart? And will they become invisible, so such a way that the computer is deciding on our behalf and and making an output. So for example, like our skin or our connected to our medical devices. I don't know. I'm trying to imagine what other smart output. Yeah, that's my question. Thank you.
Yeah, it's an interesting one. I mean, I do a little bit of research in haptics, and I can totally imagine that there's lots of ways to express output. You know, even some things that are very kind of visual, like, you know, tapping on someone's shoulder, like very like get your attention kind of thing. So, you know, clothes with haptic effects, wearables with haptic effects. There's definitely an opening there. Obviously, you know, augmented reality glasses and having sort of a personal display is possible. And we've even done a little bit of work with sound. So we did a project called digital ventriloquism. And we use these very special type of sensors called parametric speakers. It's a very, if I was in person in Auckland, and I really wish that I could be there because Auckland is a really cool city. But it's a way to actually, it's basically a sound laser. And we built a smart speaker that actually could project sounds into different parts of the room. It's really hard to describe how this works, but basically just imagine that if you had a plant in the corner of your room, we can actually make the plant speak to you. It can say, Chris, you haven't watered me in 2 weeks. And even though all the smarts are in this plant is just a plant. It has to know the direction of the plant, but it doesn't have to know anything of the plant. It's just a regular pot, nothing in there, no electronics. And this parametric speaker has the ability to project sound in the same way that a projector projects light. It actually is ultrasonic on the way there, so it's sort of inaudible in flight. And then when it hits the object, it demodulates into audible sound. And it sounds like that thing is talking to me. So I can point to a lamp and say on, and it can reply back, turning on, and it comes from the lamp. So that's a way to actually embed with audio, like a smart agent in your room. It's a very freaky technology. I mean, you can go online. Actually, there's a great guy who sells them, I think, on eBay. If you type in parametric speaker on eBay, you can buy one of these. And it's really cool to play with because the effect is really quite disturbing. It's like a ghost, essentially, in your room. So yeah, there's lots of ways to do it. This is the cool thing about HCI, going back to that earlier question, is our job is to explore these things. Now, what is the best way? Do people want clothes that tap them on the shoulder or plants that speak to them? And our mission is to explore and invent. And I think it's why it's such a fun and intellectually stimulating profession. So you guys picked the right field. Okay.
Thank you. Anyone else has any other questions? You mentioned the comment, how to observe people change their behavior when they are aware of context-aware sensors in the room.
Yeah, it's a great question and topic of interest. I mean, that's an entire PhD thesis in there. And I don't do so much with social computing, but absolutely, people are definitely going to change their behavior in good and bad ways. And we want to obviously make it as inclusive and equitable for people. Like, you know, one of the big questions that came up in our deployment of those 350 sensors in the building is, are you going to use this to track, you know, when your office is cleaned? And are we going to start monitoring the facility staff to basically optimize and micromanage them? And there's a lot of equity issues there that for these, you know, low paid workers, are we now trying to roboticize their job, that they're 5 minutes late to cleaning an office, or they take a break that they nominally shouldn't be doing? Is that actually a good thing for society? So, you know, all these are very important, and behavior change is definitely something to really consider. And that's why it's research. This is on us to think deeply about all these different subjects.
Chris, I had a quick question. So it's amazing work you're doing. I just wondered, how big is your research group, and do you have any advice or tips about how to create a productive research group? Because I think there's obviously your group is very productive, so I think there's a lot of people on the call who are postdocs who are going to be going on to other places in the future, and they'd like to learn about how you've been able to build and grow this group.
Well, I will preface this with that I think there's many different successful models. So I don't think my way is actually even necessarily the best way, but it works for me and my personality. I think it's also very personality. Labs reflect often the advisor's personality. For me, I really like actually having a very small group. I only have 3 PhD students at the moment, and my lab has at maximum had 4, and I thought that was too many. I think probably the ideal number for me is 2 or 3. And in the US, that's probably pretty small. Obviously, it also varies by country. You know, some groups in the UK are like 40, you know, PhD students. So, you know, that's a model I can't even imagine. So it's you know, there's an intersection of funding models and priorities and so on. But I like a really small group because what I love about being faculty is doing the research. I don't want to just be the guy who writes grants and then I just, have a half an hour meeting every other week with my students and I say, tell me all about the cool research you're doing. Okay, meeting's over, gotta go. I am very much a very active participant in all these research projects because I love doing research. I love the ideation and creativity and programming challenges. So I run my group much more like a team, almost like a design team. It's probably more what it's like at Apple, like in their design studio, where it's very hands-on and very collaborative and multifaceted. And it's not like I have a bunch of postdocs, I have a bunch of grad students who have a bunch of undergraduates. Even with my undergraduates, I tend to actually mentor them directly. Sometimes there'll be a PhD student involved, maybe 50% of the time, but actually probably a slight majority of the time, I work with them directly and my goal is to have them be able to produce a first authored paper themselves. So it's sort of hub and spoke model, or it's very hands-on. Maybe it's like more like a full interconnected mesh. Because I believe, good mentorship leads to good research. But the downside of this model is that's not very scalable. There are groups that publish way more than me, and they just have armies of undergrads under armies of grad students, and on a lot of metrics, they are way more successful than my lab. So I run my lab the way that I extract pleasure out of it, because as any faculty can tell you, and I'm sure that Mark can tell you, being faculty is like 100 jobs in one, and it can be incredibly stressful at times, and burnout is a severe problem in our field. So if I'm going to be working, 100-hour work weeks or 50-hour work weeks, whatever it is, as it ebbs and flows throughout the year, you got to love what you do. You have to have that passion. Otherwise, you just burn out and you're just like this burnt out cinder. So I really like working with students, and I like sitting down and hacking on code and figuring out the physics behind a problem and trying their demos and giving them feedback, because that's what I extract pleasure out of, and the mentorship as well. And so that's why I like a small group with high quality as opposed to like the shotgun approach. But again, to each their own. I don't think I've ever encountered a lab where I'm like, this is dysfunctional and totally the wrong way to do it. So that's just my recipe.
Great, thank you.
Thank you very much.
Mark, can you, I'm curious, as someone who's been in the field and published so much seminal stuff, what are your thoughts?
Oh, well, we have a very different model here, but I do like your approach. I mean, also, I know, for example, the places at MIT Media Lab, they tend to have groups of about 6 to 8 with one faculty. In my lab, we've got about 35 people across 2 locations, and it's because it's a larger group, we have to have postdocs working with those people, and it's more. I wish I had more time to spend with each of the students. So I try and get the students to work together in groups on projects, and then have as much input to the projects as I can provide. But it's challenging, and in some ways, a smaller group like you've got is easier to run and maintain, because then you don't have to have so much funding and everything else. One of the challenges, I guess, though, is that with a small group like that, it must mean that it's very highly selective for you to get a PhD student. Now, if you've only got 3 or 4 PhD students at any one time, and each PhD student's in the program for 3 to 5 years, that probably means you've only got 1 vacancy or so a year, maybe 2 if you're lucky. So that means that you if you must get dozens of students contacting you every year saying, I'd love to be your PhD student, and I guess for most of them the answer is probably no, unfortunately.
Absolutely. So yeah, if because we're also educators, and we have especially if we're publicly funded, we have an obligation to society to train the next generation of scholars. And yeah, that's absolutely a con of running a lab like that, is that the throughput is low. So it's definitely a trade-off, and that's why there's not one way to do it. And PhDs in the US typically take, I would say the average at CMU is maybe 5 or 6 years, and in HCI they tend to be 6 or 7. So we actually keep our students for an exceptionally long time as well. So yeah, I would say most years I'm accepting 1 or no PhD students. So it's very small throughput, and that's definitely a limitation of the technique. But it does help on fundraising, I will say that.
Yeah, so it's interesting models. I guess we have a whole conversation about what works in different countries. Things work differently, and of course CMU's has a different relationship with industry and everything as well. So it can be changed, it can be different. So yeah, but that's a great approach you've taken.
There's no one model, I think, is the key.
Exactly.
So
Thank you.
Find what works for everyone. Okay, I should probably drop off and grab some dinner. But it was thank you for all the fantastic questions. And I have come to Auckland in the past. In fact, I gave a talk many years ago when Professor Billinghurst invited me the last time. And so, that was probably 10 years ago or something at this point. So I hope to come again, but let's not make it 10 years in the future.
Absolutely.
Oh,
thank you.
Really great.
Thank you very much
Okay.
for the talk today, and we would love to see you again in Auckland if you come this side of the world. Thanks. Enjoy your dinner.
Bye, everyone.
Thanks a lot. Bye.